How often we find ourselves to the point of losing orientation due to the overwhelming information that is all around. If you have been there, then stick around because today we are showing some methods to compress information but the cost of losing some details. More precisely, in this video we will give a mild introduction to the so-called mathematical norms. Hi and welcome to Control Theory in Practice. Data, numbers, lot of numbers everywhere. We all know that numbers contain information, but sometimes it's just too much, isn't it? How shall we take the problem? Well, a typical approach is to aggregate them in some sort of index. Examples of indices are the inflation, the GDP of a country, the quality index, the KPI of a company, and so on and so forth. What is the effect of that? Well, the information becomes much more digestible, and let's be honest, it feels much more better to deal with just one number than with thousands of numbers, isn't it? Can you imagine when talking about inflation if instead of showing just one number, we slam a table like this to the face of people? No thanks. One interesting thing about indices is that they allow us to rank stuff, and it's funny how we, as human beings, love rankings, isn't it? Anyway, how can we create an index? Well, first of all, we have to identify some attribute of interest, then we have to establish a measurement procedure, and at the end we aggregate all the results in some meaningful way. Let's spend a few words about the measurement procedures. Although there are many methods, one popular approach is to fix a reference point and then to measure how far we stretch from there. For example, if we are measuring our height, we take our feet as a reference and then we measure how far our head stretches from there. Or if we want to measure the NO2 level in the air, we measure how its level stretches from zero. If we measure only one quantity, like our height or a specific pollutant in the air, we have just one number, so we can easily compare stuff without the need for creating any index. And therefore, writing something like this perfectly makes sense. On the other hand, if we don't specify any comparison attribute, then writing something like this doesn't make any sense. However, there are many cases where you don't have to specify any comparison attribute, simply because they are implicitly defined by the wording used. For example, if we say that John is shorter than Jim, then we are implicitly considering height as comparison attribute. Or when we say that Jim is older than John, then we are implicitly considering age. But if we just say that John is greater than Jim and nothing else, then it can mean anything, and this leaves fertile ground for misunderstanding and, worst, mystification. And this happens quite often. I can make you an example. Have you ever been in a project where the PM was periodically following up some metrics to understand and also to show how the project was progressing? And then, for some obscure reason, all of a sudden, the measured attributes or the measurement procedure suddenly changed. With that move, people had the perception that everything was going great and the project would have run fine for the next 3-4 years until someone suddenly changed job or even get a promotion. And what about the project? Anyway, back to business. As said before, claiming that Rome is better than Berlin doesn't make any sense if you don't specify any comparison attribute. But if we consider, for example, the NO2 level in the air, then writing something like this perfectly makes sense. I use the word attributes, but in control we use the word state for indicating quantities that change over time, and with the measured output to indicate the measured state. If we consider only NO2, then it's easy to compare cities' pollution. But what if we add another pollutant, like for example the PM10, in the big picture? How can we say that Berlin is more or less polluted than Rome? Well, we can arrange these numbers into a list. Then we can sum up the absolute value of each element, and ladies and gentlemen, this is our first norm. In particular, this is called one norm and it is indicated with that double bar and that little one down there. With this trick, we can say that Rome is more polluted than Berlin. Hey, but what if we believe that PM10 is more important than NO2? Then we can use some coefficients. For example, if we believe that PM10 is twice as important as NO2, then we multiply its measurement by 2, or if we believe that it's 1/10 as important, then we multiply it for 1/10. In general, you can weight norms with some coefficients that are called, guess what? Weights. Another way is to take the maximum of the absolute value in the list, and this is called infinity norm. Again, we can compare Rome with Berlin, and as done before, we can add some weights to the measurements. The result may change, of course. But we can do something more fancy. For example, we could take these two numbers, put them on a plane, and draw a segment. At this point, we can measure the length of such a segment, but hey, how shall we compute that? Well, if you look carefully, here we have a triangle where we can apply the Pythagorean theorem. So let's do it. The obtained number is called 2 norm, and we can use it as an index to measure the pollution level in a city. We can do exactly the same for Berlin. Again, we can compare the pollution between the two cities. We have now understood how we can compare the pollution of different cities when we have two pollutants. But what if we want to add more pollutants? And also, how can we deliver an air quality index like good, bad, excellent, and so on, instead of just throwing numbers? How can we do that? With our definition of norm, it doesn't matter how long the list is. If we have more pollutant, then we just add more numbers. And what about the scale? Well, we can trivially use a table. Note that we can do that for the 2 norm as well. And for the infinity norm in exactly the same way. I am sure that now someone is wondering if this is the way the real air quality index is computed. Well, kind of. Because the way the air quality index is computed depends on the region, the local authorities, the legislation, and so on and so forth. So in principle, you may have two regions close by where people breathe the same air, but the air quality index is different. Anyway, in general, real AQI is computed as it follows. We locate few dangerous pollutants, we pass them through some functions that are designed by the stakeholders that we discussed before, and we get some other numbers. For example, we pick some measurements and we end up in a situation like this. Then we arrange the result in a list and we compute a norm. In USA, they take the maximum value of such a list, which is the infinity norm, and then we map the outcome to a certain level by means of a table. I will show you now how to creatively use norms for other purposes. For instance, we can use norms for measuring the size of the gap within what you want and what you get. I'll try to explain it better. Assume that we have a pollution target for the city of Rome and some measurements. If we take the difference, then we define a gap, also known as error. Now, the goal of the measure of Rome is to take some decisions to make the actual pollution to converge to the target, or equivalently, we want the size of the error to go to 0. You can see it graphically in this way. We have a target, the actual, and the error, which is the tilt segment. We see that the tilt segment shrinks as the actual converges to the target, and that the size of the error goes to 0. In general, to make what you get to converge to what you want is equivalent to make the size of the error to go to 0. This is one of the reasons why in control we often address the problem of stabilizing the origin. Very often we mean the origin of the error. However, sometimes you cannot get what you want, but being close enough is still okay. Graphically, that means that you are fine as long as the actual lies in a region around the target, or equivalently, that the error lies in a region around the origin. To make a small recap, given a list of numbers, we have seen how we can compress them into one number by using some norm. And you can do that no matter what this list of numbers represent and no matter how long it is. However, there is a price to pay in terms of information. For example, if the equality index in Rome is bad, that's the only thing that we know, but we don't know if it is because too much No2, too much PM10 or whatever. Until now, we have seen how we can use norms for measuring the size of list of numbers, but we can use norms for measuring other mathematical objects, like for example signals. How to do that? Well, let's stick to the air quality index example and let's see how we can do that. We all know that the pollution level is not constant, but it changes with time. And this gives rise to a set of signals. Now, to measure the size of a signal, we can fix a time interval, for example 24 hours, and then we measure the area below it. This is called one norm. But, as done before, we could also take the square root of the squared value and we have the two norm, or we can just take the maximum of the absolute value, that is the infinity norm. As done with the list of numbers, we can also use signal norms to make considerations on the gap between what you want and what you get. Our goal in this case is to be as close as possible to the target. That means to make the area of the error as small as possible. However, when the actual pollution is lower than the target, it is unfair to sum this up to the error computation. To accommodate such an issue, we can trivially adjust our definition of error by taking only the bad part of the signal, namely the portion where the pollutant is above the target. The trick can be easily extended to the multidimensional case. There, we can collect each signal in a list and we can compute the norm as we have done before. To distinguish norms of list of numbers and norms of list of signals, we use a calligraphical L. And what if the signal is discrete? Well, we just replace the integral with the sum and the capital L with a lowercase l. We have seen how we can use norms for measuring the size of mathematical objects, and we limited ourselves to the case of list of numbers, signals, and list of signals, but you can define your norms for measuring the size of any other mathematical objects. However, mind that you cannot just pick any arbitrary function and call it norm, but your candidate function must pass some tests. What are these tests? Here they are. The first is that the measured size shall always be greater than 0 because it does not make sense to talk about negative sides. The size of something is always a positive number. And it is also required that the size of the null object is trivially 0. The second says that if we scale any object by alpha, then also its size scales by the same amount. For example, if we multiply each element of a list of numbers by 10, then also its norm must scale by a factor of 10. The third says that the size of the whole is less or equal than the sum of the sides of each single element. If a function passes all these tests, then you can call it norm. Otherwise, you cannot. Let's make an example. Say that we have a list made of two numbers and we define our norm candidate in this way. Let's see if we can call it norm. First requirement is that whenever you pick x1 and x2, you should always have a positive number. Here, in fact, whenever we pick x1 and x2, we always have a positive number. Second requirement is that the size of the null object shall be 0. Let's see. No, it doesn't work. Throw it away. Please, don't use this crap for measuring stuff. I hope that today you learned some more tools for compressing information. How we did compress information? Well, trivially by considering the size of objects. In fact, when you go out and you buy clothes, you can think to the size as a compressed information hiding many other details. In this video, we limited our case to information expressed in terms of list of numbers, signals, and list of signals. If, on one hand, we compress information, on the other hand, we lose details. Why? Well, because there is never free lunch. We have also seen that the concept of norm is not only limited to the mathematical object that we have seen today, but in principle you can measure the size of any other mathematical object provided that you can define an appropriate norm. In the more general thinking, when you have something, then remember that the two bars indicate the size of that something. For the sake of completeness, I just want to highlight a small thing about the selection of the weights. It is often a good idea to select the weights in such a way that sum up to 1. For example, if we take the 2 norm and we take all the weights equal to 1 over n, it's easy to see that they sum up to 1, and if we look more carefully, this is the so-called RMS value. Finally, a generalization of the norms that we have seen today are the so-called p-norms. What's that? Well, if we take the 1 norm and the 2 norm, along the same line we can take the 3 norm, the 4 norm, the 5 norm, and so on and so forth. And those are called the p-norms. So the concept of norm is very general, so feel free to use them in your project or feel free to invent new ones. With such an invitation, I'll stop here for today. For any comments, correction, insults, whatever, there is the comment section below, so please use that. Having said that, I am Ubaldo, this is Control Theory in Practice, and if you like the video, please like, share, subscribe, and so on. And see you next time.